as Greg said, so my name is Dr. Zoe Milden. I'm a lecturer here at the University of Plymouth, and my research typically is focused on earthquakes. And that's what I want to talk to you about, is partly the processes, the physical processes behind earthquakes, but also how can we actually try and forecast or predict where earthquakes might occur, and what can we do at a country level and even just an individual level to protect ourselves from earthquakes. So I just want to start off by talking about what is an earthquake, because it's difficult to talk about the sort of social side without us understanding first what are the drivers of earthquakes. So you may have seen similar maps like this before. So each of these dots indicates where an earthquake has happened on Earth in since about 2002. So what we can see is that the earthquakes are generally pretty clustered together, right? So we've got earthquakes going all the way through the oceans, and then earthquakes are much more scattered across the continents. So as Ian alluded to in his first talk, this is largely controlled by plate tectonics. So this is the idea that the surface of the Earth is made up of these giant jigsaw pieces, these rigid pieces of the Earth's crust, and they move around over time. So plate tectonics really is the kind of first order model of where generally earthquakes occur. This model, this idea, is actually only about 50 or 60 years old. And this includes some of the big earthquake zones. So San Francisco and San Andreas Fault is over here, Indonesia and the Philippines, and then areas throughout Europe, so Greece and Italy. These are all places that experience very large damaging earthquakes, which we might see about on the news. So because of this, we can broadly split earthquakes up into three different categories. So this is like a cross-section across a section of a tectonic plate. So we've got our three different types of boundaries. So we have our oceanic spreading ridge. This is where the tectonic plates are coming apart. We have a subduction zone where the plates are coming together and one is being subducted into back into the mantle. And then we have strike-slip or transform boundaries. So that's the first one I'm going to talk about, strike-slip. So a strike-slip fault, which you can model with your hands, is if you have your hands together, it's like one bit of rock sliding past the other, like that. So the San Andreas fault is probably one of the most famous ones. The North Anatolian fault in Turkey is another good example that's a bit closer to home, which I'm going to be talking about a little bit more later. And these are what they look like in the field. So this over here, this is the San Andreas fault. So hopefully you can see that this is a river channel here that's offset. Can you see that river channel is being kind of pulled apart? That's because this is the San Andreas fault that runs along there. This is another example. This is from the Kumamoto earthquake that happened in Japan in 2016. That's me there for scale. And you can see that the yellow line in the road has been offset by about a metre and a half. That's again due to a strike-slip earthquake that's coming across through here. So the second type of earthquake that we have is a normal faulting earthquake. So this is where there's extension going on, so the tectonic plates are being pulled apart. So you quite often get these at oceanic spreading ridges, but we do also get these in other places as well. So these are a couple of examples. So this is the Moab fault in Utah, the USA. So this is like a cross-section in that the fault is kind of coming out of the board, sort of towards you. And you can see from all the different coloured layers, the different layers of the rocks, that those layers are offset. In particular, this sort of quite wide kind of maroon coloured band. You can see that that's been offset as a result of the movement on the fault. A recent example is the Amatrice earthquake in central Italy, which happened in 2016. And this is a photograph. So this photograph is now looking directly onto the fault plane. The fault is the line of weakness that actually generates the earthquake. And that white stripe that you see there, that is the result of the slip in the earthquake moving that fault plane. So the back half of the photograph has gone up and the front half has gone down. And for scale, I mean there are people there for scale, it's about that high, about 1.5 meters high. And our final type of earthquakes is reverse faulting or thrust faulting. So this is where we've got two tectonic plates or two lumps of rock coming together. And some famous examples of this is the earthquake in Taiwan, which happened in 1999. So you can see this is a school running track that's been deformed as a result of the earthquake. And this is an example from the Kobe earthquake, which Ian mentioned in his talk, in 1995 in Japan. So this is like a cross-section where they've dug down into the earth. And again, the fault is kind of coming out from the board towards you. And you can, this top surface here, that's the ground surface that's been offset as a result of that earthquake. So these are the three different types of earthquakes, or three different types of plate movements or rock movements that generate earthquakes. But all earthquakes generate seismic waves. So as the ground moves, it causes, the energy of that movement causes seismic waves to be generated. And this is just a little animation to show what that looks like. So this is the western US, so this is the state of California here. And what this is going to show you is this is going to show ground movement as a result of an earthquake. So you see those coloured rings spreading out. So red means the ground has gone up, blue means the ground has gone down. So the earthquake happens in the centre here, and those waves then move out in a circular or actually spherical pattern from the epicentre. So we record these by using seismograms or seismometers. So this is an example of a seismogram in the UK, which recorded an earthquake that was a long way away. And a seismogram basically is a record of how much the ground has moved. And there are three different types of waves typically we see in earthquakes. So we have the P wave, which is the primary wave or the first wave that arrives. We then see here there's a slight change in the amount of movement recorded on this seismogram. That's called the S wave or the secondary wave. And then finally, right at the end of this record here, we've got these very, very large wiggles. This shows that the ground is moving a lot. And these are called surface waves. And these surface waves are the things that are actually most damaging to buildings and to people and to infrastructure from a hazard perspective. So this is kind of the big question. This is, as somebody who studies earthquakes, someone who researches earthquakes, this is probably the question I most commonly get asked. Can we predict earthquakes? The short answer is no. The slightly longer answer is we can start to get a feel of where earthquakes do and don't happen. Because earthquakes appear to happen pretty chaotically. Like we can't say tomorrow at 5 o'clock there's going to be an earthquake and it's going to be this big. We can't do that. We know roughly where they might occur because we can look at past earthquakes, but we don't know when they're going to occur. So locating areas of risk are known very well as a result of this model of plate tectonics. But precise prediction, and by prediction I mean an earthquake tomorrow, this is how big it's going to be, has so far proved impossible. We can start to do forecasting, however. And there's two different types of forecasting or prediction that we can talk about, or that we can look at. So one is long-term forecasting. So that's saying where the earthquake's going to be in 5 years, 10 years, 100 years. Or there's short-term forecasting, which is based on precursor signals, so initial signals that tell us there's an earthquake coming. So for example, this is an example of long-term forecasting. So this is a probabilistic seismic hazard map, where the colours tell you how the level of seismic hazard in these different areas. So here in the UK, we're coloured in green, which means the hazard due to earthquakes is relatively low. Whereas the red colours are areas where there's much higher hazard. So Japan is bright red, all along the South American margins, bright red, very, very high hazard. And these are typically based on historical earthquakes. And so that can actually cause some problems. So for example, this is the US. So up here we've got this region of high seismic hazard. This is the San Andreas fault zone, which makes sense. It's the edge of a tectonic plate boundary. We would expect there to be big earthquakes there. But you may also have spotted there's a really big, really high hazard in this area, which is nowhere near tectonic plate boundaries. So this is in the New Madrid seismic zone. So in I think it's about 1811, there was a series of very large earthquakes. Now, those earthquakes happened, they did cause damage, we know that, but what we don't know is how often would we expect those kind of earthquakes to occur? Do we expect them to happen every 100 years, 1,000 years, 10,000 years? Because knowing what the recurrence interval, i.e. how often we expect earthquakes to happen, would affect the hazard. The other problem with these kind of maps, so these maps are usually used for, to give to engineers actually to build better, more resilient buildings. So the units on this is a 10% probability of exceedance in 50 years map of peak ground acceleration. Can anyone convert that into, well, when is my next earthquake going to be? No. This is really great for engineers, but in terms of for the general public, these kind of hazard maps aren't quite so useful. One way that we can use to sort of try and start to think about where earthquakes might occur in the future is a technique called Coulomb stress transfer. And this is what I do most of my research on. And so what Coulomb stress says is that when an earthquake happens, the fault is there's going to be slip on the fault. So the rocks around the fault are going to deform slightly. And that deformation is going to induce some stresses around the fault that has the earthquake. And that's shown for an example of a strike-slip fault here. So the blue colour is where the stress has decreased, or the stress has been released from the crust. And the red zones are the areas where the stress has increased. And the idea is that the red areas, it means that there's more likely for aftershocks or future earthquakes to occur. So the classic example of this is the 1999 Izmit earthquake, which I'm going to talk about in a second. So why do we need to understand this? So Reed's elastic rebound theory, which is basically a theory about how stresses build up across a fault, implies that this line basically represents the stress on a fault, that the stress on a fault is going to increase over some time period at some known rate. It's then going to reach a threshold, have an earthquake, and the stress is going to drop to zero. And so what this assumes is that the earthquakes happen periodically. So an earthquake on a fault will happen every 100 years, 200 years, whatever length of time. But this actually never happens. There is no example of a fault where we have such periodic earthquakes. Because Coulomb stress can change the amount on a fault. So either, if the stress increases, which is shown in these little red steps here, that's going to make the earthquake happen sooner than we would expect. Or if the stress has decreased, that's going to delay when the earthquake's going to happen. So like I said, the classic example of this is the North Anatolian Fault in Turkey. So what happened here is that there's a progression of earthquakes from 1939 to 1992, where the earthquake started in the east and slowly over time moved westwards, with each earthquake occurring in a red region, so a region of increased stress from the previous earthquake. So this is the paper that was published in 1997, and what they said in this paper is that the next area to have an earthquake is going to be Izmit. No indication of time, as in when that earthquake was expected to happen, but just 2 years after this was published, there was an earthquake in Izmit. Magnitude 7.6 earthquake occurred in 1999, with 7,000 people killed and 50,000 people injured. So it's not a prediction, right? And it's not really even forecasting because there's no indication of time, but it's something that could be used, maybe with more scientific research. So, animal behaviour. This is what I get asked quite often. Oh, animals can predict earthquakes, right? So if we just monitor all the animals, then we'll know when an earthquake is coming. There's lots of anecdotal evidence about this. So this is an example from an earthquake in Canada. So watch the dog. So this is in an office block. Just watch the dog there. So the dog runs off, clearly scared by something. And then you can see that the actual office is shaking due to an earthquake. So, is the dog predicting the earthquake? Well, probably not. Going back to this picture of a seismogram, so what's going on there with all the movement you're seeing is these surface waves. Maybe the dog, which is more sensitive than humans, maybe they detected those P waves and S waves, so those first, less damaging waves coming in. Maybe. But there are problems with short-term forecasting because generally the results are very inconsistent and they're unrepeatable. And in addition, lots of people try and actually predict earthquakes after the earthquake happened. As in, an earthquake happens, and then somebody says a few days later, oh, well, I predicted that it was going to happen like 5 days ago, but you didn't listen to me. So the problem is, if we have a false prediction, then what's the cost of that? You know, what's the level of panic going to induce in the local population, disruption? You know, are people then going to believe us less if we make lots and lots of false predictions? So if we can't predict earthquakes, then we need to be prepared for them. And we can do this in a few different ways, so some of which Ian alluded to already. So one is that we can build better buildings. We can also invest in earthquake early warning systems, which can give tens of seconds of warning of an earthquake coming. And we can focus on education, so actually making people aware of the hazards that they face. Building codes are very important, because in most earthquakes, about 90% of deaths are caused by crushing or falling masonry, or crushing or falling buildings. So this is a building in Amatrice, central Italy, which had a really bad earthquake in August 2016. I took this photo in October 2016 in the main town. So this house, this was probably the top floor. You can hopefully just see there's a bed. And if you look right in this area here, you could actually see football posters on the wall. There's a little stack of school textbooks. So this is probably a young person's bedroom. And what's happened basically is that building has just completely fallen, right? And that building, that floor was completely crushed. But this is just a video again from Italy. This is what an earthquake looks like if you're not in a building. Oops. So let me just play this. So there is some sound on this as well. So they said, oh God, oh God. So this was a group of hunters that were out early one morning. That was about 8:30 in the morning. They were fine, right? They were clearly very, very scared, but they were fine because they were outside. So now they're pointing to the mountain and saying Vettoretto, which is the name of the mountain with the fault on. So the old saying, which is definitely true, earthquakes don't kill people, buildings do. That's quite a good example of that. We can also invest in earthquake early warning systems. So an earthquake early warning system is based on the different travel times and different speeds of different waves produced by earthquakes. So the first arrivals we get or the first ground movements are from P waves and S waves, and these are pretty small, and they don't make very much damage at all. In contrast, the surface waves, the ones that come later, are very, very damaging. And actually, the speed of data transmission, whether that's by fiber optic cables or by 3G networks, is much, much faster than the speed of seismic waves. So, this is an example from Japan. So, if an earthquake happens, the P waves and the S waves can be immediately detected by nearby seismometers. That can then send an alert to the Japan Meteorological Agency or any other government agency, and allow there to be an alert put out. So estimate how large that earthquake is going to be and tell people. And this can give tens of seconds of warning of strong shaking. Now, tens of seconds really does not sound like very much, but it is long enough to stop surgeries, slow train lines down, open elevator doors, and get under a table. So this is an example, a video from, I think this video was taken in Tokyo, of the 2011 Tohoku earthquake. So this is the countdown, right? So this is saying there's 22 seconds until there's going to be strong shaking hit as a result of that earthquake. So why this person stayed in their apartment and didn't get out of their apartment, I have no idea. But what you can see is the TV just starting to shake. There's usually a countdown with this, so they're actually counting down. So the earthquake early warning starts counting down 10, 9, and so on and so forth. You can see that it's shaking starting to get a little bit stronger. So that's those surface waves arriving in Tokyo. So I'm not going to play this the whole way through because this video is 4 minutes long. The shaking as a result of the 2011 Tohoku earthquake was 4 minutes in total. Most earthquakes, the shaking is for much less, so a few seconds. But this just shows kind of the level of earthquake preparedness that you can have in very developed countries. So Japan has a earthquake early warning system, as does Mexico. California's, I think, is in the process of deploying one. And yeah, even just tens of seconds can save lives. So those are some of the examples of what we can do. So trains can slow down, we can shut down manufacturing plants, stop surgeries, switch to emergency generators, even just with those few seconds of warning. And at an individual level, citizens can prepare for it. So this is a video from a classroom in Anchorage in Alaska. And you can see that those students, they know exactly what to do. So you can see that they actually only had a few seconds, maybe 4 or 5 seconds of warning, but that was enough for them to get under the table. And actually, you may have missed it, you may have not, but there are bits falling from the ceiling as a result of that earthquake, right? It's much, much safer to be under a table than it is just in the open, if you can. So most people think that if there's an earthquake, the best thing to do is run outside. That is wrong. The other thing is get under a doorway, which is great if there's only one of you in one doorway, but if we've got 300 of us and 2 doorways, not enough doorways to go around. So the official advice, if you're ever in an earthquake, is drop, very simple. Drop, cover, hold on. And you hold on until the ground has stopped shaking. And telling people this, and actually practicing these kind of drills. So they do this in California, right? You know how you all have fire alarm drills at schools? They do earthquake drills, and they practice this over and over again, so that when the next big earthquake hits, they know exactly what to do.